Okay, welcome to section 9.3. We're going to be talking about matrices and systems of equations. In section 9.1 and 9.2, we are solving systems of equations using methods that we've learned in the past, such as substitution, elimination, and then we also learned Gaussian elimination. And so we will be using matrices to perform Gaussian elimination, and what you'll see is that matrices make our lives a little bit easier. So, if we look at the example of the following system, we have 2x minus 3y equals 7, and x plus 4y equals negative 2. We can write that as an augmented matrix: 2, negative 3, 7, 1, 4, negative 2. Now, the augmented matrices that you are going to see in the book are going to have a vertical line right here. That basically is separating the coefficient matrix from the constant or answer matrix. I can't get my program to draw that in Word, so I didn't do that. So that's what I have here. So if we are looking at our matrix, each row represents the each equation. Each column represents the variable or the constant. So for example, column 1 is the coefficients of the x variable, column 2 is the coefficients of the y variables, and column 3 is the constants. And so the vertical line that separates the two, it represents the equal sign. So if we are trying to write just a coefficient matrix, it's it only includes the coefficients, and the augmented matrix includes both the coefficients and the constants. So if I wanted to make a coefficient matrix, we would only have 2, negative 3, 1, 4 in our matrix. We would not have the answers. So some more important things that you need to know about matrix. It says a matrix that is m times n, now this is also known as the order of the matrix, has m rows, so the first number is your rows, and the second number, n, is your columns. So that's going to become helpful when we go to plug this stuff into our calculators. So the intersection of a row and column is a number or an entry. These are just some vocabulary. The main diagonal of a square goes from right to left, just like reading. And remember, that's diagonal this way. So as we go down the matrice. So it says, remember that in performing Gaussian elimination, our goal was to transform our system into something like this, right? Equation 2 and 3 didn't have an x, and equation 3 didn't have a y. What would that look like in matrix form? Well, let's just go ahead and write the coefficients. So the first row is A, B, C, our vertical line, D, and then we have no x, so I'm going to put a 0 there. Whoa. Maybe I'm going to put a 0 there. Sorry about that. So we put a 0 here. Then we put E, F, G. Let me end this matrix. And lastly, I have 0, 0, H, K. So what we're looking for is we want to get these zeros in those positions. So that's what we're trying to do when we perform Gaussian elimination with matrices. So let's go ahead and look at an example. It says, solve the following system by starting by writing the system as an augmented matrix. So we're really going to be doing similar things here, except now we are getting rid of all those variables in the equations and just talking about the coefficients in matrix form. So when I start to write this, I'm going to write that first equation. I have 2, negative 1, 4, line, negative 3, 1, negative 2, negative 10, negative 6, and 3, 0, 4, 7. And so that's what the augmented matrix looks like. Now, there are a couple of things that we talked about when we were doing Gaussian elimination, and one of those things was that we wanted to have a 1 in row 1, or in the first equation. So the first thing we're going to do is we're going to switch row 1 and row 2. Now, I'm going to call these rows instead of equations now, because these are rows of the matrix. So this is row 1, row 2, and row 3. So the first thing I want to do is I want to switch row 1 and row 2. So that's the first thing. Switch row 1 and row 2. And it doesn't really matter which ones you switch, but I just started with these two. There we go. So I'm just going to rewrite the matrix like that. So this is going to equal 1, negative 2, negative 10, line, negative 6, 2, negative 1, 4, negative 3, 3, 0, 4, 7. Okay, so remember all the work that we showed last time when we were adding these equations together. Now we're not going to show work in the same way. We're going to kind of simplify life. And so the way that I kind of show my work is I draw an arrow, and then I tell you what I'm going to do. So I want to get rid of this 2 right here. And so what I'm going to do is I'm going to take row 1, I'm going to multiply it by negative 2. So negative 2, row 1, plus row 2. And then I also want to get rid of the 3 down here in the third row. So I'm going to take negative 3, row 1, plus row 3. And this is the same steps that we did in Gaussian elimination. Remember, we tried to get rid of those x's in row 2 and row 3 first. So instead of showing a ton of work, and I'll show you why in a minute, we can just do this. I find it helpful to actually write down what negative 2 times row 1 is, just real quick. So negative 2 times 1 is negative 2. Negative 2 times negative 2 is 4. Negative 2 times 10 is negative 10 is positive 20. And negative 2 times negative 6 is positive 12. And the reason why I want to do that is just, it makes it easier when I'm adding. So I have 1, negative 2, negative 10, negative 6. Now I also have, when I do my addition, negative 2 row 1 plus row 2, here's my negative 2 row 1. So that's what I'm going to be adding over here when I add that to my row 2. So I'm going to do 2 times negative 2, or 2 plus negative 2 is 0. Negative 1 plus 4 is 3. 4 plus 20 is 24. And positive 12 and negative 3 make 9. Okay, next we're going to do negative 3 times row 1. And once again, I find it helpful to write it just like I did here. So I'm going to have negative 3. Negative 2 times negative 3 is positive 6. Positive 30. And positive 18. And like I said, the reason why I like to do this is just so it's easier. It's kind of me showing some work in case I do make a mistake. So let's go ahead and add these. 3 and negative 3 is 0, just like I wanted. 0 and 6 is 6. 4 and 30 makes 34. And 18 and 7 makes 25. Okay, so now I have accomplished the first thing, which is to get the zeros here. The next thing we want to do is we want to get a 0 where the 6 is. So to get a 0 where the 6 is, I want to take row 2 and multiply it by a number so the 6 cancels out. So I'm going to take row 2 and multiply it by negative 2. And then add it to row 3. So like I said, we're doing the exact same thing we did with Gaussian elimination. It just looks a little bit easier because now we only have these coefficients. So I'm going to do negative 2 times row 2 just to make my life easier. And that gives me 0, negative 6, negative 48, and negative 18. So now when I go to add those together, it's going to be less complicated. So let me draw my matrix. My first 2 rows don't change. And 0, 3, 24, 9. So now let me just do the addition. 0 plus 0 is 0. Negative 6 and 6 is 0. Negative 48 and 34 is negative 14. And negative 18 and 25 is positive 7. Okay. So, now, what we want to do here, normally what we would do here is this is where we would do that substitution. In matrices, we can go a step further, and it really isn't that difficult. Excuse me. So now what we want to do, let me change my pen color real quick, is we want to, ooh, highlighter, let's do that. I want to change my color though. We want to get this diagonal right here. This is cool. We want to get that diagonal to be all ones. Because once they're all ones, then we have a much easier system to be looking at. So I am going to look at row 3 and look at row 2 and see what I can do to change those to having the first number, or the number in the diagonal, equal 1. And so it's pretty much exactly what you would expect. So if I have a coefficient of 3, I'm going to divide row 3, or row 2 by 3. So I'm going to take row 2, divide it by 3. And I'm going to take row 3, and I'm going to divide it by negative 14, because I want to get a 1 there. And so row 1 still isn't changed. Row 2, I'm going to divide everything by 3. So I have 1. 24 divided by 3 is 8. And 9 divided by 3 is 3. Now, I have 0, maybe 0, 0, 0. Negative 14 divided by negative 14 is 1. And 7 divided by negative 14 is negative 1/2, or negative 0.5. Now, this right here where we have ones in the diagonal is called row echelon form. Okay, so we have, maybe, I don't know why it doesn't want to write. So that's when ones along the diagonal. And that's the main diagonal, if you remember from our vocabulary. So we have the ones. So this is in row echelon form. Can actually make this go even further to something called row reduced echelon form. However, we're not going to do that right now. So if you want to rewrite this in the equations that it is and solve just like we did. So this is x minus 2y minus 10z equals negative 6. And we have y plus 8z equals 3. And z equals negative 1/2. So now we're just going to do that back substitution. So the negative 1/2 goes in for z. So we're going to have y plus, let me draw a line there, 8 times negative 1/2 equals 3. This is y minus 4 equals 3. So y equals 7. So now we have that. We have that. So one more thing to plug in. We have x minus 2 times 7 minus 10 times negative 1/2 equals 6. So 2 times 7 is 14. Negative 10 and negative 1/2 is positive 5. So we have x minus 14 plus 5 equals 6. So that becomes negative 9. X equals 15. Okay, so now we have all three of our answers. Well, we'd obviously want to write that as an ordered triple. So 15, 7, negative 1/2. And that would be our final answer for that problem. So let's kind of talk a little bit more about the matrices and what our calculators can do for us. So we did it by hand. We got this thing called the row echelon form. Remember where we had the 1 across the diagonal. So we have that 1 going down the diagonal. So that's the row echelon form. And then from there it was really easy backwards um,